Hello, I'm Ralph Gable of Electronics for the Inquisitive Experimenter YouTube channel. Today I want to do my second dive into the wild world of reactive components by looking at inductors. Because inductors span the gap between electricity and magnetism, the whole world of inductors is truly a wild world with implications and applications everywhere. They're in motors and relays and speakers and microphones and solenoids and transformers and, well, hardly a device can be designed that doesn't in one way or another depend on some form of an inductor. Because they fold in electricity with magnetism and all their interactions, the math and the physics associated with them can be wild and complicated. Now, there are a lot of videos out there that talk about inductors, and every mainstream video that I viewed either lacked the kind of depth I was looking for, or it went so deep into the topic that I needed scuba gear to plumb these depths. But as an inquisitive experimenter, you would prefer more information than these simple videos and less than these deep videos. Now, because the subject can get very, very deep, I'm going to divide my video into two videos. In the first video, I will deal with the concept of inductance more completely than most of the mainstream videos, but yet avoiding the harder to understand aspects of the why behind stuff. In the second video, I will address design type stuff. This is where I will put most of the equations like serial and parallel inductors and RL time constants, inductive reactance. But before we get into inductors, we need to cover some foundational stuff that will serve to set the stage for understanding what is happening with inductors. Because inductors straddle the fence between magnetism and electricity, I have to set down two basic principles that help define this fence. The first one is that a current in a conductor causes a magnetic field. If we have a wire that has an electric field across it because of a potential difference, then a current is going to flow through that from the positive to the negative by convention. Now, the magnetic field is going to be generated around this wire because there is a current flowing through it, and it is at right angles to the current that is causing the magnetic field. The direction of these magnetic lines can be found with what's called the right-hand rule. So you take your right hand, you stick your thumb in the direction of the current, you wrap your fingers around the conductor, and your fingers then point in the direction of the magnetic field around that wire. But what happens if we have a coil of wire, as most inductors are just some sort of a coil of wire? So we have a coil of wire with a potential difference on the coil of wire. The coil of wire is running this way, and we apply the same rule, the same right-hand rule to this coil of wire. So if the current is going around the coil of wire this way, our thumb then points in the direction of the magnetic field that is generated by that coil of wire. The stronger the current, the faster the charge is moving in the conductor, and the more powerful the magnetic field. Now, number two. The second foundational fact that we need to talk about is that when a magnetic field passes by a wire, it induces an electric field in that wire. Furthermore, physicists have discovered that the faster the magnetic field moves across the wire, the higher the magnitude of the electric field. So how do we know what direction the electric field is in and the resulting current? when a magnetic field moves across it? Well, this is where we use the left-hand rule. We put our thumb in the direction of the moving magnetic north. We wrap our fingers around the inductor, and that tells us the direction of the electric field. In this case, we end up with the plus end down here, the minus end down there, and the current is flowing in this coil this way as a result of this north pole coming in from this end down here and the direction that this coil is wound. Now that we've set these foundational facts in place, we can start talking about inductors. So what is an inductor? An inductor is an energy storage device which stores its energy in the form of a magnetic field which is produced when an electric current flows through it. The unit for inductance is the Henry. How do we define the unit of inductance? Well, a coil will have an inductance value of 1 Henry when a potential difference of 1 volt is induced in the coil where the current flowing through that coil changes at the rate of 1 ampere per second. So we have here this lovely equation, 1 Henry, and this is the standard identifier usually used for inductors, is L. 1 Henry is equal to a voltage that is induced divided by the rate of change of current in amperes per second. And this is the boiled down version, V over di dt, and you say, well, what is this? Well, let's put this in perspective in more of a mechanical way. If we talk about acceleration, and we call that A. Now, what is acceleration? You're in the car, you put your foot on the gas pedal, and you're accelerating. That is the rate of change of velocity per second, is your acceleration. I went 0 to 60 in 10 seconds. I don't know if that's good or bad, I'm not. But acceleration is the rate of change of velocity. So in the same kind of way that we write this, we can write dv dt, the rate of change of velocity with regard to time. This is the rate of change of current with regard to time. So we have a certain rate of change of current in amperes per second, a certain voltage is induced, and therefore we determine what the inductance of that inductor is. Now, let's talk about how inductors are built. So, how are inductors built? Well, because voltage is induced in any conductor by a moving magnetic field, and because every conductor creates a magnetic field around it when current flows through it, every conductor has inductance, like our friend the little wire here. This has inductance. It is of itself a simple inductor. As such, when you're talking about RF design or anywhere that you're expecting current to change abruptly, the higher the frequency or the faster the anticipated change, the more critical this becomes. Now, inductors comes in all kinds of shapes and sizes. You could have a simple coil of wire like this one here. Or here's an inductor here. You say, well, no, that's an earbud. No, that's an inductor. There's a speaker inside this which has a little coil of wire in it with a fixed magnet, and it creates your speaker. It's an inductor. How about this one? Surface mount inductors. Check this one out. You say, ah, the little dots. No, look more carefully. See if I can get it so you can actually see them. There you go. See the little black dots up at the about halfway up toward the top? Those, my friend, are inductors. And then you also have inductors that look like this. That is an inductor. They come in all shapes and sizes and power requirements and all of that. Now, with all of this said, the simplest form of an inductor is a standalone coil, like my little friend here. There I have my little inductor. It's just a coil of wire. Now we could take that coil of wire, so we have this coil of wire here, and we could wrap it around some kind of magnetically active core, such as my bar of steel here. We could wrap it around that magnetically active material, and this magnetically active material would help reduce the number of turns of wire needed to achieve a given inductance. Now, the quality of the core to concentrate and couple the magnetic flux associated with the coil is called permeability. And by the way, they don't generally use big chunks of metal like this for cores. There are many, many very specialized materials that are specifically designed for that purpose. Now, the higher the permeability of the core material, the better it is, the more effective it is at doing this job. Now, the permeability of a given real-world core material can change with temperature, it can change with frequency, and it can change with the intensity of the magnetic flux that it's exposed to. It is possible to totally saturate a core with magnetic flux if the current in the coil comes high enough to produce adequate magnetic flux to do this. So when you're choosing a magnetic core material, you have to pay attention to the frequency range for use as well as the other factors so that you can pick out the right core material. Well, like I said, shape-wise, the core of a coil could be made of all kinds of shapes and sizes, all different kinds of things. The most common for us experimenters are the cylindrical type cores and the toroid type cores, or donut shaped. This is a toroidal core. Now with variable inductors, what they'll do is they'll take a coil much like this, and they'll have core material that they will put in and take out. They'll actually have a means of inserting the core material and bringing the core material out. In some cases, what they do is they put a threaded inside on these, and the core material then has threaded outside, and the core material is then threaded into the coil, and it has a means on the end of the core material, so you can get a tool on there to actually turn this in and out of your coil. In some cases, and this is the odd case, you don't generally see this, but they do have variable inductors that actually have a little guy that makes contact with the coil, and they pivot the coil, they rotate the coil, and that little guy rides up and down and chooses a different number of turns off of the inductor for a variable inductor. Now, you have the toroid, and one of the big advantages of a toroidal shape is that the magnetic flux, by and large, tends to be mostly confined to the inside of the core. It makes shielding a lot easier. And the way they use this, the way they wrap these, is your wire goes around and around and around through the center of the core, around and around and around, using the entire circumference of the toroid. So your coil would start here and move its way around the coil or the core and exit down here. So the wires come out at the bottom. Now, with that, we need to be able to calculate the inductance of an inductor, or we need to calculate the number of turns that we need to create a particular inductor. And so we're going to start talking about formulas associated with inductors. Let's talk about formulas now. Now, with a simple inductor, which is just a coil of wire wrapped around some kind of a form, the amount of inductance is determined by the number of turns on this particular coil, the overall length of the coil, the diameter of the coil. And now I need to make an important note about diameter, because we are not just talking about the diameter of the form that it's on. We're actually talking about the diameter of the form plus going out to halfway through the wire. So you need the coil form diameter plus the wire diameter, so you're actually getting the diameter to the center of the wires that are wrapped around that form. And then the permeability of the core, and I need to make a note here, this is called the relative permeability of the core, and that's relative to free space. Now, there are a lot of equations out on the internet. If you go out and look at the internet for equations for a single layer inductor, you're going to see a lot of variations. And most of these will bear some resemblance to each other, but there are some significant differences. In some cases, they just simply leave stuff out, and it becomes just a rough approximation of the inductance. Other big differences to watch out for is they speak of diameter or radius. And I noticed in some cases they talked about the radius of the coil, and the same rule applies. If they're talking about radius, they are talking about the distance from the very center of the coil out to this halfway point in the middle of the conductor that's out there. So they'll talk about radius. They'll talk about dimensions. The dimensions might be in meters, they might be in inches, they might be in centimeters or millimeters. The original physics equations that all of these boil down to, the final equation we have here, are all in meters, because that's what physics operates in. So you have to pay attention, look for, well, what are the units that they're using? Some overtly include the permeability of free space into the formula, and others bake it into the formula. You say, well, permeability of free space. Well, there's the actual permeability of the core material is the relative permeability, mu sub r, times the permeability of free space. Well, this here is a constant. So a lot of times this will be boiled into the equation that you end up with, and sometimes they have it outboard of the equation. So with that, here's the formula for a single layer inductor with everything in inches, and I've baked mu zero into the equation. So we can calculate the inductance of a coil, a simple coil of wire, using this equation. We have the inductance in henries is equal to the diameter of the coil. Now remember, This is from the center of the wire on this side to the center of the wire on this side. The diameter of the coil squared times the number of turns in the coil squared. Now, divided by 18 times the diameter plus 40 times the length of the coil times your relative permeability. So I didn't include all the decimal places in these values, because in the end you're arrived at value, no matter how many decimal places you use or how carefully you wind the coil, that arrived at value is only going to be a close approximation to the real value, which means tuning required. And the easiest way to tune an inductor like that is to purposely wind it with a little bit of space between all of the windings on your coil, and then adjust the length by moving the windings in order to change the inductance to kind of hone it into the value you really want. But if we look at this equation, we can see that if the number of turns increases, then this value increases. In fact, look at this, and the number of turns is squared, so that means if you double the number of turns, then you quadruple the inductance. And then you have the length of the coil. The length of the coil is down here at the bottom. If you're keeping turns the same, the diameter the same, and all you're doing is making the coil shorter or longer. In other words, you're changing the turns per inch of this coil. Then because this is on the bottom, if the length gets longer, the inductance gets lower. If the length gets shorter, the inductance gets higher. Now comes a little bit of tricky here with the diameter, because when you change the diameter of a coil, if you keep the number of turns on that coil the same, and you keep the length of the coil the same, then that means that if your diameter is larger, the circumference of that coil is larger, requiring more wire to wind the coil. So if we keep this the same and this the same, and only increase the diameter, then the inductance increases. Notice here, the higher the core permeability, the higher the inductance. Well, maybe you've heard that inductors oppose the change in current. If you haven't, then inductors oppose the change in current. The big question is, well, how do they do that? Well, it's all about the magnetism. Well, let's consider an inductor. Here we have a coil, and a long time ago in a galaxy far, far away, a constant current started flowing through this inductor. We have some kind of battery or potential source here. The current is flowing through here. We can do the right-hand rule as we look at the direction that things are flowing here, and we can see that the North Pole is down here and everything is stable, and there it is. So with this constant current is a constant magnetic field. Nothing is changing, everything is great. The more current that we put through here, the greater this magnetic field, the stronger it is. The less the current, the less the magnetic field. Now, what happens if we start to change this current in the inductor? Now, if the strength of the magnetic field is determined by the amount of current through the conductor, then if we reduce the amount of current, then the magnetic field is going to begin to collapse. Now, it's collapsing because it's not as strong as it was. But in the process of collapsing, these magnetic field lines are passing across the inductor itself. Now what happens if we have an inductor and we pass a magnetic field through it? What happens to it? It generates an EMF, a potential difference across itself. And the faster that magnetic field moves, the more powerful that electric field is that's induced in it. Well, here we have a current changing. The current is going down, let's say in this case, the magnetic field is collapsing across this, which means it's moving across the very coil that's producing itself. But the conductor doesn't care whether it already has a current flowing through it. The conductor doesn't care where the magnetic flux is being generated or why it's moving. All it knows is that, hey, I have a magnetic field moving across me. I need to generate a potential difference. So what happens? As current goes down, the moving magnetic flux essentially creates its own battery to try to maintain the electric field across itself so that the current doesn't change, so that the magnetic flux doesn't change. And if we're increasing the current, now this north pole, it's moving the other direction, and now our battery flips around, so we have the positive side here and the negative side here. Now with this going up, the magnetic field moving away, now we have the battery in the opposite direction, trying to maintain this potential difference, to maintain this current, to maintain this where it's at. So, because the speed of the movement of the magnetic field affects how much potential difference is introduced into the conductor, the strength of this effect is frequency dependent. This frequency dependency is referred to as the inductive reactance of an inductor, and that introduces yet another equation which we will cover in the design rule stuff video. Now, I'm going to give you a brief word about transformers. Transformers are nothing more than magnetically coupled inductors. And that means that you can have two magnetically coupled inductors or more. I mean, there are transformers out there with multiple taps and secondaries. The primary side is the, you might want to call this as the input of the transformer, or the primary. And then the transformer has one or more secondaries. And these secondaries, they could do fancy things like put a center tap in the middle of here and have it a coil here with a center tap, or multiple taps even on one winding, or they could have several secondaries that are completely independent of each other. There's lots of different ways that they do this, but essentially there are two or more inductors that are magnetically coupled to one another. And so let's just think through this real quickly. You have on the primary side, you have current being chunked into this primary side, and it's a time varying current. So let's say we're running at 60 hertz. This is a power transformer of some flavor. So now the current is doing this on this side. It's going up and it's going down, and it's going up and it's going down. Now, what's happening? Let's think about the magnetic field. Now, as this is going up, the magnetic field wants to get stronger because there's more current going on. More current, stronger magnetic field. As the current goes down, the magnetic field collapses and starts going in the other direction, so it's moving in the other direction. Oh, but now the current changes direction. So now, if this was the north end, this now is working at becoming the north end, and this becomes the south end, and the magnetic field once again begins to grow, just opposite polarity, and it reaches a peak, and then it starts to come back down again, and it goes the other way. So now what we have is this moving magnetic field across a conductor over here, this inductor. And if you have a moving magnetic field across an inductor, you have voltage. And so you have induced voltage in this secondary side because of the moving magnetic field. And so you will see on this side an induced voltage. Now, there's all kinds of transformers out there, and because remember, the core material, the suitability of a core material depends on the frequency that they're to be used at. So that means that this core material has to be the right stuff, and the transformer has to be designed for a specific frequency range for them to be used at. You can't use a power transformer that's designed at 60 hertz for your 100 megahertz RF at all, because it's just not suitable core material. It just won't work. So if we happen to have more inductance associated with this secondary than we do the primary, then that means, let's just say that, this is 10 turn or 20 turns, and this is 200 turns. Well, guess, or 200 microhenries. Well, now you see the difference. The output voltage is going to be higher than the input voltage. But what if we did the other way around? We had 20 microhenries here and only 2 microhenries here. Now the voltage is going to be lower. It's going to be a step-down transformer. So the step down or step up or 1-to-1 is determined by the turns ratio between the input and the output. And that is how transformers work. So we've completed the first in the series on understanding inductance. Like I said, it's a wild, wild world with so many variations, so many applications. And part of what makes it really wild is the connection with magnetism. It is 1 foot into the world of magnetics and 1 foot into the world of electric fields and so on. So it's just a crazy world with lots of complications and applications. You just find them all over the place. I've attempted in this video to give you the foundational truths behind how inductors work. What is an inductor? How are they built? Some formulas that relate back to how they're built and how to calculate the inductance or the number of turns for a particular inductor. And then finally, how do they actually work? Taking these foundational truths and kind of boiling them down into an understanding of how it opposes the change in current. In our next video, we will be covering all of the design related stuff. So we'll be talking about inductors in series and parallel and the RL time constant. We'll be talking about inductive reactance and why does the phase of current lag voltage in an inductor, and what about real inductors made with real stuff. In the meanwhile, thanks for watching. Toodaloots.